So let's say, I'll just give you an example. Let's say there is a simple question of a block like this. Okay, of a
Yeah.
incline, there is a block here, block A. Let's say the mass is m, and let's say the height here is h. Okay, and this is angle theta. Acha, okay, tell me one thing. Uh, let's say this is ground, and a mass m, a mass a, which is a block A which is having a mass m, is raised up to a height of h. So what is the potential energy stored in this block?
MGH.
All right. So mgh is the potential energy stored in the block. All right.
Yeah.
So let's say block m, it is moving with the velocity v. So what is the kinetic energy of the block?
Yeah. Half M V square.
All right. So this you know, and you also know the conservation of energy, right? That the total U plus K will be constant all the time. All right, no. So like the total potential energy of a body and the total kinetic energy of a body, that is also called as the mechanical energy of the body. Okay, no, that remains constant. They may change from
Yeah.
one part to another part, or maybe potential energy can get changed into kinetic energy, or some of the kinetic energy can get changed into potential energy. But the
Mhm.
thing is, the sum of these two will be constant. You know this. So now the thing is, see, this is just an introduction. We'll come to all those things again in this chapter. Now I
Mhm.
just want to solve you this question. Okay, I just
Mhm.
want to want you to give me the answer. What will be the velocity of mass m when it reaches here?
I couldn't hear. Can you repeat?
What will be the velocity of mass m when it reaches? You are able to see the figure, no?
Yeah.
When it reaches to the bottommost part, what will be the velocity of mass m? So this is the block A, and you know the forces and all. So and this angle theta is already given. So I just wanted to know what is the velocity you are going to get of
Does
mass
it come
m.
to stop or
No,
it's
it doesn't
like
come to
does it come to
stop.
stop?
No, it doesn't come to stop. You just don't imagine that there is a ground there. It is just getting released from there. So if it is getting released from there, what is the velocity when it just leaves the end of the block, end of the incline? I don't want you to solve like that. What I want you to solve is I want to want you to solve it by the usual method. How you are going to
Hmm?
do? So there will be an acceleration, right? And the initial velocity will be equals to zero.
Yeah.
You know,
Yeah.
right? You know, right? The forces are there. So this is the
Hmm?
incline.
Hmm?
So there is a normal contact force,
Yeah.
and there is a mass. There is mg here. So and the
Okay.
block is moving in this direction. So how we are going to write the equations? So this is angle theta. So this is angle theta.
N is equal to mg cos theta. Mg sin theta is equal to ma, right?
Right. So mg sin theta will be equals to mass into acceleration. So what is the acceleration you know now?
G sin theta.
So acceleration of the body is g sin theta. Can you get with the velocity? What will be the final velocity? So initial velocity is this, acceleration equals to g sine theta. Height
Yeah.
h is given. So what is the total length there? Distance equals
S
to?
is equal to your ut plus half at square.
Yeah, that is okay. But what is the s actually? You, what is the distance traveled before it reaches here? What is this distance? You know h, this is h no already. And
Yeah.
this is theta here. So what is this distance? See, this is h, this is theta. What is this? You have a triangle, right? One side is given h and the one angle is given. Can to get the hypotenuse there?
So we have to consider this side as B, like anything.
Whatever you consider, I just want the answer in h and theta terms. Why is it so difficult for you? These things. This is not the part of the question at all.
H by sin theta.
Okay. So you know the distance traveled, right? You know the distance traveled no, now?
Yeah, I got.
So h by sine theta is the distance traveled. So
Hmm.
s is equals to h by sine theta. Now you want to find the final velocity. How you are going to get it?
V square is equal to u square minus 2as.
V square is equals to u square plus 2as.
Yeah, sorry, plus 2as.
Okay.
We know u square is equal to 0, so plus 2 into 2gh. So
2,
root 2gh nothing but
2g
uh,
sine theta
yeah,
into h.
sin theta.
S is what? H by sine theta, right? Right, no, 2 s. A g sine
Yeah.
theta. So the answer is 2gh. So v is equals to under root of 2gh. Now you can see in this equation, you can see one thing. that this velocity doesn't depend upon the mass at all. So whatever was the mass of the body, if it falls the same distance, it's going to have the same velocity. Right? No, it doesn't depend on the mass at all. That is one thing.
Yeah.
The other thing is, now since we are studying the chapter work and energy, we'll try to solve it by work and energy. So work and
Okay.
energy
Yeah.
theorem says that the potential energy stored plus the
Huh?
kinetic energy of the body remains constant. Okay, so
Mm.
what we do is, the potential energy, for potential energy always we have to take a reference plane or a reference level.
Mm.
Okay, so we assume that this is the reference level where the potential energy is equals to 0. So since this is
Yeah.
height
Yeah.
h, so the potential energy at this level will be equals to mgh.
Yeah.
And we assume that let's say the block reaches here and has a velocity v. Okay,
Okay.
and
Mm.
since it was at rest here, so kinetic energy here equals to 0. Right, no? So the
Okay. Yeah.
total energy here, the total energy here will be equals to what? Total energy here, I mean the mechanical energy, right? So the total
Mm.
energy here will be equals to mgh
H
plus
plus
0. That
V
means
plus.
mgh. And what will be the
Yeah.
total energy here? That will be equals to 0 plus
Half
potential
and
energy is 0 plus half into mv square, right?
yeah.
So we know that this total energy has to be conserved. So mgh, the initial energy, all right, no? So initial energy is equals to the final energy, the conservation of energy theorem.
Yeah.
So mgh is
Mm.
equals to half mv
Half
square.
and V square. Yeah.
So if you see this, it was very easy that v is equals to under root of 2gs. So it was very simple to solve it by
Yeah.
this method. So a lot of questions of the Newton's laws and where generally friction is not involved can be solved by using the concepts of work and energy also. First thing you can see in your book, the first thing given is the kinetic energy, right? So we are studying work and energy. So we just gave an introduction to you that how this work and energy can be useful in solving questions, and that too very easily. Okay, instead of using all those formulas s equals to ut plus half at square and all, you can directly use work and energy theorem to get those things. So the thing is, in case of all those free falling bodies and the first thing which we studied, no, in the kinematics chapter,
Mm.
right, where there was no friction involved and the bodies were simply falling, or you can say that the bodies were moving in a straight line, those things can all easily be solved with work and energy. So first thing is, what we'll see is what is kinetic energy. So kinetic energy is equals to half into m into v. So that is
Yeah.
basically, you just forget it, you just understand it is half mv square. So it is dot
Mm.
product of velocity. So since the angle will always be equals to 0 only, so it's going to be half mv square only. So this is the first thing you can mark in your book. So there will be a lot of markings coming in your book. So those things will be important. So you can always refer only those points in this book and you can just move ahead. So you can mark the first formula in your book. So that is 8.1, I think.
Yeah.
Now the thing is, there is 8.2 also given, but I will not like you. I just don't want to let you confuse now. So just leave it. So when it comes, we'll see.
Mm.
Okay. Now the second
Yeah.
thing is, we'll define. Let's say a force is acting on a body. All right. No. So
Mm.
we'll define work done. What is work done? All right. No. So let's say a body is there. Okay. And let's say a force F is acting on it. All right. So let's say this body has moved a distance dr, a small distance dr. It is moved now. All right. So let's say this body has moved a small distance dr. So what we say that the work done, the dw, the small work done dw has been done there, and that is equals to f dot dr. So
Ah.
f dot dr is that means if you just integrate it, you will get this. So total work done will be equals to actually integration of f dot dr.
Yeah.
All right. So the
Ah.
force vector and the displacement vector. So the dot product of that will be the work, the total work done. Basically, what it means, no? Let's say there is a body here, and you
Mm.
are applying a force in this direction.
Yeah.
Okay, and what basically has happened is, let's say this body has moved here up to 5 meters at an
Mm.
angle of, let's say, 30 degrees.
Okay.
All right, no. So
Mm.
basically, what this equation means is, we do not want we do not consider the movement in the other direction. We consider the movement only in the direction of the force. All
Mm.
right, no, so that is 5 by 2.
Mm.
All right, no, 5, sorry, 5 root 3 by 2, huh?
Oh yeah, 5
So that is 5 root 3 by 2. So the work done will be basically force into 5 root 3 by 2 here. This is
Okay.
newtons. All right, no, so basically when you do this, this will also come the same thing, force into the displacement vector dot product. So dot product is what? So this is force vector and this is the displacement vector here. All right, no,
Yeah.
so this is theta. Okay,
Mm.
so what is dot product? F dr cos theta, right? So if you
Mm.
see this, this will come the same, right? So 5
Yeah.
into cos theta is root 3 by 2 here. All right, no.
Mm.
So basically, what
Yep.
this work thing means is the force and the displacement along the direction of force.
Mm.
All right, now you can simply remember what the work done is dw equals to f dot dr, or you can simply say that
Yeah.
this is the work done, the total work done by a force acting. The thing is, again we'll come back to the 8.2 equation now. Okay, so what you can see here is the dk,
Mm.
the small change in kinetic energy is equals to f dot dr.
Small change.
In kinetic energy is equals to f dot dr. We'll see how it comes. So if you see
Mm.
if you see kinetic energy k is equals to half into mv square,
Yeah.
right? So if you get the change rate of change of kinetic energy, how much you are
Mm.
getting?
The radiation in kinetic energy.
We are differentiating both the sides. Okay,
Okay. Okay.
so 2v, right? So this becomes,
Half to be. Yeah.
right, no, so this becomes
Yeah.
what?
MV.
So this will be dv by dt because we don't know
Yeah.
velocity right now.
Yeah. Yeah.
So this becomes
So
mv
M dV by dt.
dv by dt. And what is dv by dt?
Like rate of change of V with
Rate
respect
of
to
change
speed.
of v is what? Acceleration, right?
Yeah. 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 Okay.
Okay,
Acceleration.
so m into v into dv by dt. So dv by dt is
Mm.
acceleration, right?
Yeah.
So if you see this part and this part, this is
Mm.
mass into acceleration, right? What is
Yeah.
that? That is force, right?
Mm.
So force, and this part is we know already, force into velocity,
Mm.
right? No,
Yeah.
but basically you have to remember for the time being that this force will be the tangential force. Tangential force basically means along the direction of the motion. So this is the
Yeah.
velocity. So this is the direction of the motion force also. So if this is the
Mm.
force and this is the velocity, then this ft comes into picture. Okay, no. So the tangential
Uh.
force. Okay, just don't get confused that much.
Mm.
So we don't know which direction the force will be. So let's say if we just want to know the tangential force. Okay, so you can or what you can do simply is you can just forget about these things. It's just a derivation, so you do not focus on this. You just have to remember
Mm.
the theorems right now. So let's say dk by dt becomes fv now, and this v can be written as dr by dt. So if you
Yeah.
see, and this is tangential force, you just remember that this is tangential force. That means component of the force. Let's say the velocity direction is this, and force direction
Okay.
is this. Okay,
Mm.
so we need a component of the force in the direction of the velocity.
Okay.
As I
Okay.
just told you, no, for the in the example of work done.
Huh?
Right, no,
Yeah.
so
You told
similar
me.
way, it's like the component, the force and the velocity should be having the same component. The force and the displacement also has to be having the same component. So the force and velocity is same component in the case of kinetic energy, and
Mm.
force and displacement should have the same direction in the case of work done. So just forget about this. Just see this one.
Okay.
So this dk can be written as,
Yeah.
because this
Okay.
becomes actually f dr cos theta, no? So this f cos theta,
Mm.
f cos theta basically is the tangential force,
Mm.
right? No, the force along the direction of the tangent. I mean along the direction of the motion. I can just give you a best example here that let's say a body is moving in a circular motion, no?
Mm.
Okay, so let's say the body is moving with a speed of 5 meter per second. So this is the
Yeah.
direction of velocity.
Yeah.
Okay, and if you see the direction of acceleration, let's say this is a uniform circular motion. If you see the direction of
Mm.
acceleration or the direction of force, it is perpendicular to it. So the force direction is not tangential, right?
Mm.
If you see the velocity here again, so the same velocity 5 meter per second is there, but the direction of the
Okay.
force is again tangent perpendicular to it. right?
Uh-huh.
No, it's not along the direction of the velocity. So if you see
Hmm.
the kinetic energy in a circular motion, the kinetic energy is constant here.
Hmm.
Even though the velocity is changing, but since the speed is not changing, the kinetic energy is
Yeah.
always constant because the body is moving with a constant
Hmm.
speed,
Yeah.
right? No, so the same
Yeah.
logic you can apply here, that the
Hmm.
force, the direction of the force should be in the direction of the velocity for the kinetic energy to change. Understood? No, in the case of a uniform circular motion, the direction of the velocity and the direction of the force are not the same direction, right? No, they are not tangential at all. They are at 90 degrees. Okay, so there will be no component of this force in the direction of the velocity, and thus the speed is not changing. The velocity is of course changing because the direction is changing here. Right,
Okay.
direction of the speed is changing. No, so that means velocity is changing. But since the speed is not changing, the kinetic energy remains constant. And
Yeah.
for
Okay.
this, for the kinetic energy, you can understand that the force should always be in the direction of the
Uh,
velocity. Then only there is a change in kinetic energy. So basically, from this equation, you can see
yeah.
that dk is equals to f dot
Hmm.
dr. So
Can you repeat what you said?
dk is equals to f dot dr.
Yeah. Yeah. Okay. Okay.
Right
I'll
now,
write
so
that
you
down.
can see that dk is equals to dw. In the
Hmm.
previous one, that the work done is equals to dw is equals to f dot dr, right?
Yeah. Yes, Uncle. Understand.
Right, no? So
Yeah.
basically, just forget all those derivations right now.
Hmm.
Whatever we just wrote, you just forget it. It's of not
Hmm.
much use. You just mark it in your book. There is written something like thus the work done on a particle by the resultant force is equal to the change in the kinetic energy. This is called your work energy theorem. So this is your
Okay.
work energy theorem. You can mark that. So this is your work energy theorem. We just saw that the change in kinetic energy is equals to the work done on the body. Alright.
Okay.
So
Yeah.
work done on a particle by the resultant force is equal to the change in kinetic energy.
Work done by a particle by some force is equal to the within kinetic energy.
Right now, equal to the change
Yeah.
in kinetic energy, right?
Hmm.
Okay, this is called your work energy theorem.
Hmm.
Now let's solve a question.
Hmm.
Now what I want you to solve is, let's say there is a body. Let's say there is a body of mass m. There is a constant force acting F here. Okay,
Hmm.
and let's say at a point when this was moving at a speed v here, I want you to solve this. That let's say it has traveled for 10 meters, and I want you to solve what is the velocity v2. Let's say we'll give you numbers also. So let's say this velocity v is equals to 5 meters per second initially. Okay, and the force was acting, a force constant force of F equals to let's say 10 newtons was acting on this, on the mass m is equals to let's say 5 kgs. Okay, and let's say the block has moved a distance of 10 meters. After the block, what after the block has moved a distance of 10 meters, what will be the final velocity? So you can do this in your, huh?
There's no
There is
friction.
no friction. So work energy theorem will not be valid
Hmm.
when there will be friction. All right, no,
Okay.
work energy theorem will be valid. I'll tell you when we proceed. No, there is a very strong point regarding friction in this chapter. Okay,
Hmm.
so when we proceed, I'll just let you know about those things. So we are
Hmm.
just ignoring friction here. There is no friction acting on it.
Hmm.
So there is a force only that is equals to 10 newtons,
Yeah.
and there is no friction. The initial velocity is given. What is the final velocity after 10 meters? So what will be your
Hmm.
usual way? What will be the usual way of solving this?
Same thing. We can just use W is equal to F into dr.
So what is the work done?
Work done is force into yeah.
Right,
Time.
both are in same direction, so no
Yeah.
need of dot product and all. You can directly multiply, right? So that is
Huh.
equals to 100 joules. So I am sorry, here it has, I have written newtons, so it is joules. So the unit of
Hmm.
work done will be joules. Okay,
Yep.
work done and energy both will be same. You have seen, no,
Hmm.
change in energy is equals to change in kinetic energy is equals to work done, right? No, you just see this, work done is equals to 100 joules. Now what is the initial kinetic energy?
Half m v square. Half m v square. 5 e to 25. Yeah. Nothing
Okay,
but 1 to 75. No. No. 62.5.
okay, let it be 125 2, right?
Yeah.
What is the final energy, kinetic energy?
Half into 5 into x v2.
V2
Okay.
square, right?
Yeah.
Now what?
We have to equate these two.
So work done is equals to,
Change in kinetic energy.
so what is change in kinetic energy here?
Okay, half into v square, v2 square.
Half into
No, no, first this comes, yeah. Yeah,
final
half
minus
into,
initial. See, change is always final minus initial.
yeah, minus 25, 125 by 2.
So this way you can get your velocity, right?
Uh,
Right now, so this is one way you can do using the work energy theorem, that the total
yeah.
work done on the body will be equals to change in the kinetic energy, that you can use here and do, right?
Mm, mm,
The usual way you could have done the other way which you have been doing in the previous chapters is, you could have solved and you could have got the acceleration first. So acceleration
mm,
equals to force by mass. So force is 10 newtons, mass is 5, so acceleration will be 2 meters per second square, right? No, so you know that the distance is equals to 10 meters, initial velocity is equals to 5 meters per second, and you know the acceleration equals to 2 meter per second square, and you can get the
mm.
final velocity. So this is also one way you could have done,
Okay.
right? No, so this is your one way you could have done this. This is your another way in which you are using changing the kinetic energy, right?
Mm.
Understood?
Yeah,
So
good.
that part you have to mark, that is called the work energy theorem. Okay, so that is
Mm,
your first part. Now the
mm,
second thing what you can mark is,
mm.
just below that you can just see that, thus the work done by the resultant force is equal to the sum of the work done by the individual forces.
What? Okay.
In the same page, last statement that is written in italic, no,
Uh,
that you can mark in your book.
uh,
Work done by the resultant force
mm.
is equal to the sum of the work done by the individual forces.
Yeah. Can you repeat again?
Work done by the resultant force is equal to the sum of the work done by the individual forces.
Hmm.
We can just see this by an example.
Yeah, okay. Okay.
So let's say a block is there. So let's say a block is there. There are two forces acting here. Let's say force F1 and let's say
Huh?
force F2.
Yeah.
All right. And what has happened is this block has moved a distance of, let's say, R.
Hmm.
Okay. So the work done, if
Hmm.
you see individual work done by F1, how much it will be? F1
Uh,
vector dot R vector. And work done
hmm.
by the force F2 will be how much?
F2 vector into R vector.
Dot R vector. So basically what you could have done is, you could have
Hmm.
taken the resultant of these two forces, right? Now
Hmm.
let's say there is a force F which is the resultant of these two forces.
Yeah.
So basically what you would have done is, you would have taken, understood that this body has moved a distance R,
Hmm.
okay, and there is only one force acting on this, which is equals to
Yeah.
F. And this basically, this F means what? This is the resultant of these two forces, F1 and
Hmm.
F2. So this F what we have written there is the resultant of these two forces. Understood? No, let's say this is 5 newtons and this is 10 newtons, and there the angle between them is 60 degrees. So you can find the resultant, right?
Yeah, yeah.
So it may not be in the same direction what I have drawn. It may be in a different direction also. So this may
Yeah.
be like somewhat tilted also. So let's say this is the resultant force.
Hmm.
Okay. So what you can do is that the work done here you can calculate simply by F dot R, right?
Yeah.
So what this theorem is telling is, F
Hmm.
dot R is equals to F1 dot R plus F2 dot R. That work done by the individual forces, some of the work done by the individual forces, that is or the total work if you want to calculate the total work done, what you can do is you can just individually sum all the forces acting on the body, okay, all the work done by those individual forces, or you can take the resultant of all the forces and just find the work done by that particular resultant force.
Yeah, okay, yeah. Understood.
So this is another the second point which we have to remember. So
Hmm.
till now what we have done is work energy theorem we have studied, that the
Hmm.
total work done on a body by the resultant force, all the forces combined, is will be
Hmm.
equals to the kinetic energy.
Yeah.
Alright, no, that also means that if there is no force acting on a body, the
Hmm.
kinetic energy is not going to change.
Oh, okay.
Right, no?
Yeah. So more force, no, like, I mean, the kinetic energy remains the same.
No force. That is very obvious that if there is no force, there is no acceleration, so the velocity will
Hmm.
be same, and that's why the kinetic energy is not going to change. That
Yeah.
is one thing. The another thing
Hmm.
is if the work done by all the forces equals to zero.
Hmm.
Let's say there are forces acting on a body, but the total work done by the forces is equals to zero. Then also
Hmm.
the kinetic energy is not going to change.
Okay.
See, things will start getting difficult as you go on, chapter by chapter. So that's why
Okay.
I've been asking you to solve as many problems as possible.
I see.
All right, no.
Uh-huh.
So as we saw that the change in work done, the change in kinetic energy is equals to the change in work done. I mean the work done, right? No. So if
Hmm.
work done is not equals to zero, there is no kinetic energy change.
Hmm.
That is one thing. If the force is equals to zero, then also the kinetic energy change is equals to zero. Why? Because if the force itself is equals to zero, then there is no work done.
Yeah.
Then again the kinetic energy equals to zero.
Hmm.
You can understand this in a different way. If the force is equals to zero,
Hmm.
the acceleration is equals to zero because force is equals to mass into acceleration.
Hmm.
Acceleration equals to zero, that means dv by dt is equals to zero.
Hmm.
That means there is no change in velocity, right? No, this is what rate of change of velocity, no?
Hmm.
dv by dt means what? Rate of change of velocity,
Hmm.
right? No, so there is no change in velocity.
Okay. Okay.
Since there is no change in velocity, what is your kinetic energy? Half mv square. So since
Hmm.
velocity is not changing, we are not studying the variable mass here. So only velocity was there which could change. Since the velocity
Hmm.
itself is not changing, the kinetic energy will also not change.
Hmm.
Right? No. So
Hmm.
basically, when the total work done on a body is equals to zero, the kinetic energy equals to zero. I mean, the change in kinetic energy will be zero. So there will be no change in kinetic energy. That was the
Okay.
work energy theorem, which was saying
Yeah.
that work done on a particle by the resultant force is equal to the change in kinetic energy. If there is some work done, there will be change in kinetic energy. That was the first theorem. The next
Uh-huh.
theorem what you studied was the total work
Hmm.
done by the
Huh?
resultant force
Hmm.
is equal to the sum of the individual work done by the forces. Let's say if there are
Okay.
more than one force acting on the body, you
Huh?
can individually, for all those forces, you can individually calculate the work done, or
Huh?
you can take sum of all those forces and then calculate the work done. Both will be same. You're getting
Hmm.
my point? I gave you example also, right?